Um, roughly, we're not going to cover quite 15 or 16 chapters. We're going to cover about 12 so.
So it would make sense to go slower through some parts?
Yeah, there will be some parts that we definitely will go slower through and cover in more details.
Will we be hitting? Will we be going through electricity in the second part of this class or the first?
Second semester.
How about
Yeah, so in the first semester of this class, we will not cover fluids or thermodynamics at all. We won't cover sound, but we will cover waves a little bit, just because we need waves to go into the second semester a little bit. So we'll cover waves a little bit at the end of this end of this semester, but we won't cover thermodynamics or sound or any fluid mechanics, stuff like that. As the farthest we'll go is we'll go into rotational mechanics, and we'll cover a little bit of the statics, and then we'll do waves. And so let's see, in this book, that means all these chapters in this book, which are, well, no, not quite. So we'll go all the way through to, so we'll go all the way through to 12, and then we'll jump forward and hit, in Unit 2, we'll hit waves. Well, maybe oscillations and waves. So I guess it'll be about 14 chapters. So it'll be fewer chapters than weeks, and we'll have a little bit of time to cover some things in some chapters a little more in depth.
which do you think would probably be the area where we would cover more in depth, most likely?
Very likely in chapter 4, and very likely in chapter 6, probably. A little bit extra time, maybe even somewhere along in here with the momentum and energy, but more very likely in 11.
Yeah.
Angular momentum can get very involved in 3 dimensions. So,
I remember before, and I guess it was just 2 dimensions it was kind of.
yeah, it can get pretty tricky. I'm not entirely sure how much we'll go into chapter 12 and chapter 13. There's some stuff that's interesting there, and we probably will try to go in depth in a couple of things there, but I'm not sure. It'll be essentially 1 chapter a week in the end. Well, it'll just be a little bit more here. Most likely we won't go over a week in any chapter, but some chapters on Fridays we'll just kind of say, do you have any questions, and let you go.
Right.
So
It seems like in the beginning, it might be, we might go quicker through the material, but it might be easier.
yeah, so we've almost covered 2 chapters. We've covered 2 chapters in just over a week, and we should finish chapter 3 probably this week. We'll probably finish chapter 3 on Friday. So
That'll give us a good time.
Yeah. We'll probably be completely through chapter 4 next week, and starting chapter 5 the Monday after that. Next week, of course, we have a short week because no class on Monday, but that doesn't really matter because we don't think we'll need the entire week to cover chapter 3, or chapter 4. So yeah, in the first 3 weeks, we'll be done with 4 chapters, and then from then on out, we'll have a week for each chapter, and hopefully by the end of the semester, we've got a week or 2 of time where we can pick a subject and do a project or something fun, that kind of thing. That's what I prefer to do in this class, because every other class is cramming for finals and all their difficult stuff is at the end, where in this class it's mostly the difficult stuff's in the middle, in the beginning. So it's mostly about the learning curve of getting used to dealing with vectors and calculus with physics. So yeah, it'll be a very different. Hopefully we'll have a different kind of class where we have some time at the end to spend some time doing something interesting, applying the things that we've learned.
We're recording class, right?
Sorry?
We're recording class, right?
Yes.
Okay,
Class is now being recorded. Yes, indeed. So, anyway, so today we're going to start our study of kinematics, and fairly fairly straightforward stuff, except that if you've taken this class before, you may not realize that we have. I guess I actually don't need to do that. Hold on a second. Let's end this meeting. Don't actually have to open a meeting. I just need to share my screen. I guess I do need to have a meeting if I'm going to share my screen. Okay, so that's fine. So let's share the screen with the whiteboard. Okay, so here is our coordinate system that we, usually we start off with a rectangular coordinate system with our x pointing off to the right and our y pointing up like that. That's just kind of standard. You see that pretty much everywhere you go, anything you're doing. Start off with this. And if you have a vector that's going to tell you a position, first of all, you need to know the position. So let's say our position is out here at this, let's say that this is at coordinates 5, 4 or something like this, right? Well, there is a vector that is going to go from the origin out towards that point and then point at that point. That's not a very good pointing at that point. Make the point bigger. It's hard to draw on this thing. I've really considered buying a pad, but I haven't found one at a decent price that I like yet.
I have some pretty affordable routing options at about like maybe 100 or 200. They have
Yeah, but they don't all connect with your computer is the
some
problem.
of those.
Some of them do, but not all of them. I haven't found one that I like yet. So eventually I'll find one that I like, and then I'll start using them. But anyway, we've got a point out here at 5, 4, and we've got a vector that points to that point, and that is actually a position vector, right? We usually name our position vector R, the vector R. You'll see that quite a bit. Unless we're in one dimension. If we're in one dimension, then you're only going along one axis, like the x-axis. And then we usually call that vector x, just because it's one dimension. So if you only have a position in one dimension, then your position is somewhere along the x-axis. Of course, if you have the two dimensions and your vector is r, there are going to be components to that vector. There's going to be an r sub x component and an r sub y component. And the r sub x component, of course, will be 5 times I hat. And the r sub y component for this vector would be 4 times j hat.
Whenever they use the R instead of the vector, does that usually imply that it's always going to be related to trigonometry in some way?
Yeah, usually when they use r, they're usually talking about a two-dimensional vector, so that you're going to have to use some trigonometry at some point. Unless you're, if you're in rectangular coordinates, you're going to have to use some trigonometry eventually. If you're in polar coordinates, maybe not. Maybe you can just leave things as they are. But, that usually does denote that you're in two dimensions. So right now we're in one dimension in the book here. And so in one dimension we're going to have two things, a final position and an initial position. And these really could be denoted as vectors. It could be like right here they're showing a displacement vector going from the initial position to the final position, but you could also draw vectors from the origin out to your initial position and from your origin out to your final position. And you would actually, if you subtracted those vectors from each other, final minus initial, you would get this displacement vector, even doing the graphical version of it. So position vectors always go from the origin out to the position, and displacement vectors are different because they always go from the initial point to the final point. Okay? Or from initial position to final position. However, that gets a little confusing because the definition says you take the final and you minus the initial, subtract the initial, right? It's final minus initial, not initial minus final. But that's true in any case of vector mathematics. When you calculate a vector or the magnitude of a vector by taking the final minus the initial, then the vector always points from the initial to the final. That's the way it goes. That's the way it is in vector mechanics, vector mathematics. So that's just something to be aware of. But this is the definition of displacement, and it is a vector. It does have a direction to it. And right here they showed you that direction from initial to final. And it is, as all vectors are, it is a straight line. You don't follow the path that they take. It is a straight line from the initial position to the final position, no matter what path they take. They could be going from San Francisco to New York, and somebody who goes from San Francisco to New York directly goes in a straight line from one to the other. But somebody who goes via Mexico City does not go in a straight line to New York, right? But their displacement vectors are the same. The distance they traveled is different, the path they took is different, but their displacement vectors are the same. Incidentally, what happens if you go from San Francisco to Chicago back to San Francisco? What's your displacement vector? 0, right? Even though your distance is thousands of miles, your displacement vector is 0 because your initial position and your final position are the same position. And anything minus itself is always 0, right? So whenever you end up where you start, your displacement ends up being 0, even if the distance you traveled is a long ways. If you have multiple displacement vectors, you can also add them all together to equal a total displacement vector in one dimension. That's simple, because you're just going forward, backward, forward, backward, whatever else, and you end up at some place, and all those things add together to be a displacement vector. In 2 dimensions, not so simple, but we'll learn about that later. Still true. So, displacement is our first definition. Our next one is going to be velocity, and here they're calculating essentially just magnitudes of these things right now. We're not talking about the vectors yet so much. But it is a vector. Velocity is a vector. It does have a magnitude and a direction. And the way to calculate your average velocity when you're traveling or moving is to take your displacement and divide it by the time that it took you to go through that displacement. So it's x2 minus x1, or x final minus x initial, and divide that by the time final minus time initial, and you have your average velocity. Now, why is that an average velocity? Anybody have an idea? You could be going different speeds in between points. In fact, for practical purposes, you will always be doing that. There's no such thing as going at constant speed all the time. There's always some variation, right? You go from here to Kearney in an hour, then you're speeding, right? At some point, you're speeding. But we don't really know how much you're speeding. You might start out at 60 miles an hour and be going 150 miles an hour somewhere in the middle, and then end up at 60 miles an hour and slow down to 0 or whatever. But at some point, you have to be speeding because your average is going to be 100 miles an hour, right? It takes 100 miles to get there. Take the distance divided by the time you get the average velocity. The direction of the velocity, of course, is determined by the displacement vector, essentially. Your average velocity between 2 points is going to have the same direction as the displacement vector between those 2 points. So, since it is defined by the displacement vector divided by time. So, average velocity is displacement divided by time. Displacement has a direction, so velocity has that same direction. Here's an example where Jill is setting out to deliver flyers. She travels due east on the line between her houses, 0.5 kilometers, 9 minutes later she runs out of flyers, has to retrace her steps back, takes another 9 minutes, picks up some flyers, goes back again, right? So here's this is where it becomes kind of useful to draw a picture, because you can see what's actually happening. She goes out, she comes back, she goes out, she goes back, and then she goes past her house, actually. And so what is her final displacement? Her original position is here. The final displacement is over here, right? Or final position, or initial position, final position. So her displacement is actually going to go from her house to the east instead of to the west, right? This is east, sorry, this is west. We said east is positive, so we're going to say that's east. So this is east, this is west. Her final position is to the west of her house. And they say that west is negative since east is positive, so it's going to be a negative displacement vector from home to her final position. And if we want to know that distance, we can do some simple arithmetic. You have 1.75 kilometers from here all the way back here, but it's 1 to here, so you subtract off the 1, so it's 0.75 from her house to her final position. Or you could add these up. This is 0.5 minus 0.5 plus 1 minus 1.75, which gives you negative 0.75. Either way, it works out. And they do it in the table here and give you this final position and everything else. They also make a chart of it, going forward, backward, forward, backward. And the interesting thing about making the chart, of course, is that from the chart you can calculate what? This is a position chart. And up here we learned that velocity is change in position over change in time. So this is position versus time, right? Yeah, I don't think you've gotten to this yet in your calculus class, but in calculus you learned something about something called the derivative. How many of you are familiar with the derivative? So if you're just starting calculus, you may not be familiar with that, but the derivative tells us the change in some function relative to the independent variable. In this case, the independent variable is time, right? So the change in x relative to time. Well, change in x relative to time is essentially the slope of this graph. And that tells you the velocity. So it tells you the velocity during this time is positive because this slope is positive. But the velocity during this time, this chunk of time here, is negative, right? And it's because they turned around and went back to their house. So this one is positive 0.5 over whatever this is, 10 minutes. So positive 0.5 over 10 minutes, or a little bit less, 9 minutes, right? And this one looks like it's about negative 0.5 over about 9 minutes. And this one looks like about the same slope, actually. So it's about the same slope, positive, about the same slope, negative. Right? So the velocities look to be similar here and here, and similar here and here. However, the average velocity is going to be also affected by how long you are walking at a particular velocity. And this one here is the longest one. And then you have this one added on to it. So these two are going to dominate. Our overall velocity, our average velocity, is going to end up being negative because these two are going to dominate the average. And we find out that that's true, that the overall velocity, average velocity, in this problem is negative 0.013 kilometers per minute, turns out. Because they take the total displacement divided by the elapsed time. Much easier to take the average by just taking the initial position and the final position and plugging them into this equation, right? Final minus initial over the change in time just gives you that negative 0.013. But you can see why it works out in the graph, using a little bit of understanding of calculus. So, how do we determine the velocity at a specific point in time? Instead of saying what the average is, which is fairly easy to calculate, how do we calculate the velocity at a particular instance in time? And this is where we get more involved with the calculus. If you have a car traveling from here to Kearney, let's say, and you measure its speed all the time, you measure its speed every second, every tenth of a second, every millisecond of its travel, doesn't matter what it is, you're going to end up with some kind of a curve. Now this is a position versus time curve. So let's say we're measuring the position of the car every fraction of a second, every tenth of a second or something, right? Of course you can't measure anything continuously. It's impossible. Every measurement takes time. So every time that you take a measurement, the time that you're taking it, you're not taking a measurement the next little bit of time, right? So if your measurements take a tenth of a second, then you can only take 10 measurements per second, right? And in between those measurements, you're not taking measurements. Anyway, the point is that here we're taking a bunch of measurements of a car that is apparently going to go somewhere, and we're trying to figure out something from it. So here's our first measurement, here's our second measurement, our third, or fourth, or fifth, or sixth, or seventh, right? Or sixth, rather. 1, 2, 3, 4, 5, 6. 1, 2, 3. There's 7. Oh, they're calling that T0. I don't know why. But anyway, there are 7 measurements that we take at 7 different times, and that's great. However, your average velocity is always going to be measured between two of these times. So if you measure the average velocity between t1 and t2, you're going to get this slope that's kind of steep right here. But if you measure it between t1 and t6, notice how different that slope is. It's going to be a very different velocity that you measure. And that's because you didn't know that it sped up during the time that you were waiting to take your next measurement and then slowed down again. Not only did it speed up here and reach reach some kind of, I mean, this right here was this was actually its maximum speed. So it sped up right here, then it slowed down a little bit, then it slowed down a little bit, then it stopped, but then it turned around. Up here, it's actually going the opposite direction, turned around and came back. Because these are negative velocities, it's going in an opposite direction, and negative slopes, right? So you didn't even know that all that happened, so it really changes the slope. Right here, you think it's going super fast. Here, it's going pretty slow. Right? Because it turned around and came back. So the closer you can get these times together, the more accurate your speed will be, your velocity will be at that instant, right? That instantaneous velocity. If you can get them closer and closer together. The way that we do that in mathematics is using this little trick called the limit, right? So you have a whole bunch of measurements that are close together like this, and you make them closer and closer together by saying the delta t, which is how close together those times are, that change in time, gets smaller and smaller and smaller. It goes to 0. So we take the limit as delta t goes to 0, and we look at this function. Now this is a very common function that you will see in calculus, mathematics in general. I can't remember the name. It's named after somebody. But it's essentially a difference function, they call it. So you take the value of the position at some time plus some change in time, and then you subtract off the value of that function at that original time. So this tells you the difference. What this is going to tell you is going to tell you how much this thing has moved forward right here and upward. Actually, it's going to tell you how much it moves upward. The thing down here tells you how much it moves forward. So this function right here will actually tell you the slope of this line at any given point, as long as you take that limit as delta t goes to 0. What does it mean as delta t goes to 0? Well, you say, well, in this math, what happens when delta t gets closer and closer and closer and closer to 0? A lot of people would say, well, this is going to go to infinity because you have this 0. This ends up being 0 down here. That's not exactly what's going to happen. There is some theory behind all of this, and you'll get to learn that in your class, in your calculus class. But in the end, what this tells us is it tells us how much things are changing from a single point. If you go left or right or whatever, doesn't matter which way you go. It just tells you what that is. And we call this thing the derivative. This is how we denote the derivative in time. The derivative in time is d by dt, or d divided by dt. Mathematicians hate when you say d divided by dt, but it does end up looking like this, d dt. And most times when we're talking about it, we call it d dt or d by dt. So it's the derivative with respect to time, in other words. And then if you put that in front of something, like they have it here, the x of t is right here. That means what this all means, and how we say this, is d by dt of x, or the time derivative of the function x. And we have a t here because we're saying that x is a function of time. But this is the time derivative of x, or d by dt of x, and some people even call it dx dt, and that's fine too. Another way that this is denoted, particularly in physics, because in physics we hate writing things that are not necessary all the time. We often write just a function and put a dot over it. That's something that you will see in physics and engineering quite a bit. That's called, then they just say it's x dot. X dot means the time derivative. That specifically means the time derivative. No other derivative is written that way. But because we use time derivatives so often in physics and engineering, we just have a shorthand for it. Makes writing it down easier and cleaner. So this is the time derivative, and what that is it's a way of calculating the slope at any particular point along a curve, along a function, calculating that slope. And you can do it in multiple dimensions as well. You'll learn more about that later in calculus. You'll actually learn a little bit more about it in physics first, and then you'll learn about it in calculus later. So if you have a graph like this, and this is your position function, and you want to find out the velocity, well, the way to find out the velocity at any given point in time is to find out what the slope is at any given point in time on the position graph, right? And this is easy. You can just read this slope off the graph. Where is this thing stopped? Where is the stopped position on this graph? The horizontal line. It's stopped between about 0.6, or that's 0.6, 0.5 seconds. So it stopped at about 0.5 seconds, and it started up again at about 0.10 seconds, which would be 1 second, right? It would be about 10 tenths of a second, or 1 second. If you plot the velocity, you'll get a 1 and then a 0 and then a negative 0.5, because the slope of this is about 1. If you go from the beginning, since it's a straight line, we can calculate the slope by taking the end minus the beginning. The end is about 0.5, the beginning is about at 0. And then the time is 0.5, so it's 0.5 divided by 0.5 is the slope of that line, which is 1. And then this one ends up being about 1 to 2, so it's about 1 second. And it happens in, sorry, it's about 1 second, and it goes half a meter. So this one's about negative 0.5 over 1. So it's negative 0.5 for that one. So, and of course the slope up here is 0. So this is the velocity time graph. You graph those slopes. And of course, what is the velocity at 0.5 seconds? Can you take the slope at a point that has a corner on it? You can't really, right? You can't really tell the slope at a corner. And that's why we know this isn't realistic. You can't just go from having a velocity of 1 to having a velocity of 0 without slowing down. It just doesn't happen. There is no possible way to do it. So a more realistic curve would have this thing curving a little bit at this junction, and curving a little bit at this junction, which means that on this graph, it would curve down and then it would curve down, right? In reality, that's what it would be. Textbooks aren't always in the realm of reality. So if that's what if velocity has this definition that is displacement divided by time, and it has a direction, then why don't we just call that speed? Well, because we give speed a different definition. Speed is the distance divided by the time. So it cares which path you took. If you went to Kearney, but first you went to wherever, Chadron, whatever. You go to Kearney, but on your way you went up to Chadron. Well, you're going to go a lot longer distance going to Chadron and then going to Kearney. Tons longer distance, right? And that means that your total distance divided by your time is going to be a higher speed because you have a higher distance. But if you go to Kearney and don't tell anybody that you went to Chadron first, they're going to say, why did it take you 8 hours to get to Kearney from North Platte? You must have been going, 100 divided by 8, 16 miles an hour the whole way. Well, no, it wasn't. I was going 75 miles an hour the whole way. I just went to Chadron first, right? So it can be confusing. So speed is going to be that total distance divided by time, which gives you a real idea of how fast they were going, quote unquote, during their travels. And also will probably give you an idea of how far they actually traveled getting from point A to point B. Right? In Nebraska, it doesn't really change much. When you're going somewhere, you usually go in a straight line. But if you go through the mountains of California or the mountains of Utah or the mountains of Oregon or Colorado, it's zigzag back and forth craziness all the time. And so it can really affect your total distance, even though your total displacement is quite small. Your distance can be quite big. And if you want to know the instantaneous speed, then you need to actually know the instantaneous velocity and take the magnitude of it. That's how you know the speed at any exact point in time, because this equation up here is still an average. Give us some nice ideas of speeds in meters per second compared to miles per hour, right? And so you see here that cycling, some people will go 10 miles an hour. That's not a cyclist. That's more like somebody riding their bike to elementary school, 10 miles an hour. But a cyclist, might go twice that. But you can see that in meters per second, it's about 4.4. So the relationship between meters per second and miles per hour is about double. You take your meters per second, you double it, and that's about how many miles per hour you're going, ish. And that's close to that. So that kind of gives you a nice idea, I think. If I'm saying you're going 50 meters per second, you say, well, that's about 100 miles an hour. That's moving along pretty fast, right? All right. Speed of light in a vacuum. So this is the ultimate speed limit of the universe. 299,792, 458 meters per second, which is a lot, right? 500 million miles an hour. And only things that have ever been clocked going anywhere close to that speed are very, very tiny particles and, of course, light itself. There are some other things, actually. Gravity waves have now been measured, and they are clocked at known speed of light as well. The speed of the Earth around the sun. Did you have any idea how fast the Earth moves around the sun? It's pretty fast. This is how fast you have to be going to escape Earth's gravity. 11,000 meters per second. Pretty fast. Excuse me. So, anyway, this right here. They're going to give us a short lesson in derivatives. So, if you're trying to calculate the time derivative of a function of position that is a function of time. So, because this is your velocity. This is how you would calculate your instantaneous velocity, by taking the time derivative of your displacement vector. But let's say that your displacement vector x of t is some polynomial. So a polynomial always has some term in it, a times your independent variable t, and the t could be raised to some power. Let's say the power is to the n. ATN. You should do it ATM because then it's an ATM. If you're going to take the derivative of this, the time derivative of this, so d by dt of x of t, I should probably do this on the computer. I keep forgetting. The way that you do this, and this is essentially just a trick, it's just a shortcut. It's not why this happens, it's just the way to do it. I'll leave the why to your calculus teachers so they can get paid for doing their job. So what you do is you take the density. What's that? Oh. Anyway, you take this number that's up there in your exponent of your independent variable, and you bring it down in front as a multiplier. And then what's left up there is going to be whatever you had minus 1. You subtract 1 from it. So it's like you just took one of them down. Right? And that's what this formula is telling you. You take you're starting off with this function AT to the n. You bring down the n as a multiplier, and then you subtract 1 from the n in the exponent, and then that is the value of that derivative. That tells you what it should be. Let's do a couple of examples really quick. So if I tell you that my displacement function, so this is essentially a mathematical function that describes this curve. Let's say that my displacement function looks like this. 2x cubed minus x squared, right? Something like that. That means that my displacement function looks kind of like this. This curve looks something like, I don't know exactly what it looks like, but something like this. You know, it's going to be shifted around a little bit and have different heights on things, but it's going to look something like this. Okay. So if it does look something like this, then you can go along in here, and this is the time, and this is my position in x. So this is going to tell you the position in one dimension of the particle. So at time equals -4 or something, then my position up is like 6 up here. At time equals 0, my position is 0, right? And sorry, this is incorrect here. I did this wrong because I wasn't thinking clearly. It's too early. I've been up too long. I've been up since like 5 something this morning. So I have an excuse. This is actually t instead of x, right? Is that right? X is a function of t, yes. That's my independent variable. That's my function. There we go. So that should be t. My bad. So anyway, the point being here is that once you plug in a time, if you plug in time equals 0 right here, and right here you get 0, so that's why it hits right there, right? If I plug in t equals -4, then I get -4 cubed, which is for 64, right? Times 2, which is 128, minus 16, which is a lot bigger than this. So this needs to be a lot steeper, right? So this is like 100 and something at -4. And but if I go out to, sorry, that was, no, -4 should be negative. It should be down here, actually. Like that. But anyway, it doesn't matter what the curve looks like. The point is that it represents some curve over here, and this thing will tell us what those values are going to be, right? So you've got this thing here, but what you want to know is what's the slope of this thing look like? Well, that's what the d by dx or d by dt is going to do. D by dt is going to tell us the slope of x. So how do I do that? Well, it just told me that I take the thing that's up here in the exponent and put it down in front as a multiplier, so 3 times, and then I put the 2t to the cubed, and then I subtract 1 from the 3 up here. And then I do the same thing in this one. I just put this one down, I write this one down as -2 times t squared minus 1. So I brought my multiplier down, my 2, I left the negative stays, I bring the 2 down, and then I subtract 1 up here. So this ends up being, in the end, 6t squared minus 2t. And that's the slope. This right here is the slope of this at every point. So this is my velocity as a function of time. This tells me my velocity. So if I want to know the velocity at 7 seconds, I just plug in 7 seconds into this function and I'll get my velocity. So for some of you, that's your first derivative. Congratulations. This is the rule for polynomial derivatives. Other types of derivatives are different. For example, the derivative of the sine is very different. You can't take the derivative of the sine and get some polynomial out. It's just not, it's not correct. So it turns out the derivative of the sine is actually the cosine, right? The derivative of the cosine is the negative sine, right? So, and then if there's something inside of the sine, besides just t, then there's some other rules for that. And you'll learn those rules as you go through calculus more. That's really what calculus is about, is memorizing and applying rules. Which is why I think calculus is one of the easiest classes I ever took. Like, algebra was way more painful. There's not just a few rules you memorize and then you apply them. There's like, you have to look at this thing and say, what am I going to do to solve this piece of crap? But anyway, like calculus 1, calculus 2, calculus 3 was just memorizing and applying, memorizing and applying. And then calculus 4, it's like algebra with calculus. And you're like, oh crap, algebra again? And not only that, but you have to guess at the answer a lot, which you have to guess and see if you're right.
You're talking about differential equations?
Yeah. Yeah, differential equations is like it's one of the worst math classes I ever took, because the whole purpose The whole thing with that class is, well, look at the problem and try to guess what the answer might be. Check it and see if it works, and if it doesn't, use what you learned from your wrong answer to get the right answer better next time. And then guess again and try it again. Oh my goodness, and nobody even told me that till the end. I was trying to like solve these things. No, it's really just guess, make your best guess and try it out, see if it works. That's really all it is. There's no other way to do it, and that's like, there's like equations named after these famous people who were really just guessing until they got it right. People like L'Hopital and D'Alembert and whoever else, all these French and Russian mathematicians. We used to call them the dead Frenchmen. All the dead Frenchmen of calculus. Okay, so anyway, what happens though if we have this situation? Let's do a very simple situation now. What happens if we have our position function is just -2 times time? What is our derivative? You guys do that one. What's the derivative of -2 times t? This is what the graph looks like. Kind of like that, right? So what is the derivative? What is x dot of t? It's constant, -2, right? And that's always true when you have a constant slope in your position function, because a constant slope in your position function means that you have a constant velocity. So this constant velocity, x dot, is just -2, because you take the 1 down out of the exponent for t, which is 1 times -2, and then you take 1 minus 1 in your exponent, you get t to the 0. T to the 0 is of course 1. You get a bunch of 1 multipliers and you're done, right? What happens if we have x of t, our position in t, is equal to 7? What's the derivative in time of the function 7? 0. Because if this is 7t to the 0, you bring down the 0 multiplier, you get 0. The derivative of a constant is always 0. If your function is constant in the variable that you're taking the derivative of, then it is 0. The derivative will be 0. So this one has 0 velocity because its position is constant. Its position is just sitting there at 7 all the time. It's just 7, right? Extremely important to remember, but it's also extremely easy to forget. It's important to remember what the derivative does. And when you're taking a calculus class, you get caught up in the how to do a derivative instead of what it means. Right? So don't get too caught up in how to do the derivatives. The really interesting thing is that in calculus, they're going to teach you a million different ways to do derivatives. In real life, there's only a few things that you need to know. Only a few of those are actually applicable in real life. Most of the derivatives that you do over there will never ever be used by any human being to actually do something in real life. So don't get too caught up in it. Learn what you need to learn, get through the class, get a good grade. And then, go back to physics and engineering, and you'll learn a handful of derivatives that have to be learned because they actually apply in real life. But the derivative of the polynomial is definitely one of those, because you can make any function into a polynomial with using some techniques of approximation. You can approximate any function with a polynomial function. It's just how approximate is it, right? So, and that's really what's important. So you definitely have to learn this trick, the trick with the polynomials, and a few more tricks will be helpful as we get further into this. Okay, so let's go back to our book here. Here they do some examples of these, and they also plug in numbers. Once you have a function for a position or a function for a velocity that is a function of time, then you can just plug in the time you want to know the position at, or the time that you want to know the velocity at, and that function will actually calculate the time or the velocity for you, which is nice. And there are some problems like that in the homework. So here they're just doing more of that average velocity or the instantaneous velocity at a particular time or whatever else, or the average velocity, average speed over the entire thing, whatever. Just doing more examples of that. You'll see more of that in the homework. Ooh, we're just about out of time here too. The last thing I'm going to tell you really quick is that the acceleration is also a derivative. What is it a derivative of? Can you guess? It's a derivative of the velocity, right? So down here, the acceleration, if your velocity can be written as a function of time, then your acceleration is a derivative of that velocity, right? Function. So the acceleration ends up being the slope of the velocity curve. And all the same things apply. So we will study this in a little more detail Friday. Tomorrow we'll have our lab. You guys, of course, are exempted from that having done the lab. But we'll see you guys tomorrow at 10, right? 10 o'clock for lab. We'll do our first lab experience. Still trying to decide how much calculus I put into the laboratory experience, because I have these labs that are calculus-based that I really like, and there is a calculus version of them, but I think it takes a bit longer. So we'll see how we do it with it. So